Welcome learners to the course on electron device, and today we'll start our journey on the optoelectronic devices. We start the course on solar cell as because of the shortage of our duration and we have to cover up our courses in a relatively fast manner. So I will consider rather the important topics on the subject of electron devices, and today start with the solar cell. Myself, Arpon Deashi from the Department of Electronics and Communication Engineering in RCC Institute of Information Technology, India, welcome you all to the course on the optoelectronic devices. I think all the learners are today aware about the importance of the solar cell because the renewable energy is a growing demand in the market, and several renewable energy options, that means the several sources are explored day by day. Several investments, big projects are going on, and the most familiar one among all the renewable energy sources is the solar cell. Though there are several options like the biomass, wind energy, tidal, ocean, geothermal, several options are available, but solar cell has its own importance because solar energy is one of the freely available energy and require less mechanical cost to make a big solar array compared to the other mechanical infrastructural cost available in case of other renewable energy sources. And the physics of understanding of solar cell is relatively easier for the electronics engineers and the physicists because it starts with the basic concept of the junction diode and its analysis. So the people of physics, people of electronics, as well as the people who are interested in the renewable energy can start with this course. And in this context, I may also make one point that if you are interested in other renewable energy courses, you may visit to my YouTube channel where there are other options are available, and also the application part of the solar array, the solar collector, and the basic solar time calculations. Every lectures are available, so you can browse it, you can go through, and you will get, I think, the initial study materials. Also, in my SlideShare account, some slides are available on the different aspects of the solar cell. You can browse through it, the solar cell physics, the calculations, different calculations, I think solar array, solar collector, everything is available. So you can also get some information in a digital mode. So let's concentrate on our today's topics, that is solar cell. So why people are mostly interested in solar cell and why it is more or less familiar? If I want to analyze it, let me start with our journey in the electromagnetic spectrum. So I think you know all about the electromagnetic spectrum, and starts from the gamma rays and goes to the radio waves, the frequency modulated wave, amplitude modulated wave, and so on. And in a very small region you will find our visible ray, violet to red. I think everybody knows it. So if we broadly categorize the different regions of the electromagnetic wave, then we can mainly focus four different regions. One is ultraviolet, which is very close to our visible range. I think if you go slightly lower wavelength of visible, then you can go to the ultraviolet. Then visible blue and visible red, these are two major visible portions, and if you slightly increase the wavelength you will go to the infrared. So in the table below in this slide you will find that ultraviolet wavelength lies from 10 to 400 nanometer, visible wavelength lies from 450 to 490 nanometer, red varies from 635 to 700, and infrared goes from 1000 to 10,000. So I have also mentioned what is the corresponding energy, and naturally it will be in the electron volt scale. So for ultraviolet, it varies from a wider range, from 3 electron volt to 124 electron volt. It's a very wide range. Whereas for visible, it's 2.53 to 2.76. For red, it is 1.77 to 1.95. And infrared is from 0.124 to 1.24. Those are the standard energy ranges. Now the question will come, why we are interested with these wavelength ranges and as well as the energy ranges. That means what are the consequences of it? So if I just look a little bit details in this table, that means if you just make a introspection, you will very easily find that the ultraviolet radiation part can safely be omitted. It can't reach to our Earth's atmosphere. Why? Because the ozone layer present in the top, it totally absorbs the ultraviolet radiation. Though in several newspapers and in several technical articles and reports are published, now the thickness of the ozone layer becomes thinner, and that's a deadly thing for our civilization. But still, ozone layer safely absorbs the ultraviolet. So if I remove that part, then our starting range varies from 0.124 micron to within 3 micron range. Electron volt range, that's the energy. So the energy bandwidth, if that is the range available for solar radiation, then we require some materials to absorb this solar radiation. And what are the materials? The materials should have a band gap, varies from 0.1 electron volt to 3 electron volt. Now, if the material has a band gap in a moderate range, it should be semiconductor. You can't go for conductor or you can't go for insulator. Because 3 electron volt is a high band gap semiconductors, and 0.1 electron volt is a extremely low band gap or narrow band gap semiconductor. So ultimately you have to take semiconductor material in order to absorb this solar radiation. And the material should be extrinsic semiconductor, because intrinsic semiconductor is insulator, so you require doped semiconductor. So what I am trying to do within these 3 slides to help you starting your journey from the electromagnetic radiation spectrum, choose our required spectrum, and for the required spectrum, what are the materials required in order to useful absorbance of the spectrum, that's given. It's a qualitative understanding that we require extrinsic semiconductor, may have narrow band gap, may have wider band gap, may have moderate band gap in between them, but that's the requirement of material if we want to utilize the solar spectrum. So based on this fundamental formulation, I want to proceed, and for that our total criteria for device design, for its analysis, will be solely dependent on the physics of the extrinsic semiconductor characteristics, its electrical performance, optical performance, and so on. And one point in this context may be noted down that since it is an extrinsic semiconductor and our input is optical energy, naturally solar radiation, that means sunlight, will be the optical energy, and our required output in the electrical form. So we have to design a device whose input will be optical, output will be electrical, and it will be based on extrinsic semiconductor. Again, I am repeating, we have to design a device whose input will be optical, output will be electrical, and it should be made by extrinsic semiconductor. So that requirement is already established with a very minute observation on our visible ray and the corresponding spectrum close to our visible range. So that's our prerequisite in order to proceed for device design and other parts. I think this portion can be easily understandable for all. So what is solar cell? If you look out the picture as shown in the slide, this is nothing but the incident ray. It's shown the incoming solar radiation, whose 4% is reflected by our Earth's surface, 20% reflected by clouds, and 6% reflected by atmosphere. So if you add 4 plus 20 plus 6, that means 30% of the solar radiation is already reflected back. You can't use it. Also, 19% of the solar radiation is absorbed by cloud and atmosphere. So almost 50% is gone. So rest of the 50% is sufficient for us to make a renewable energy source. And for that, we require a semiconductor device which converts sunlight into electrical energy. And why it is required? Because it is free, because it is non-polluting, and it's readily available. So all these 3 points which I have noted by bullet means are under the characteristics of a renewable energy source, and that's why if we can design a device in order to effectively utilize the 51% of solar radiation, then that device will be considered as a non-conventional energy source or a renewable energy source. So I am basically looking from the application point of view. For that requirement, we will make a device and go to its analysis, and that will be our physics. So my objective is whatever the requirement for the civilization. In order to satisfy the objective, we have to design a device, and that approach will be followed in rest of the part of this video lecture. So our effective target is to utilize the 50% of the solar radiation. And why we will utilize it? Because it is freely available and it is non-polluting in nature. So these are the 2 fundamental points related with the solar cell. In order to get that, we have to understand the physics of the photoelectric effect. So what is photoelectric effect? If you look out the device I have shown, it is basically nothing but you are absorbing the energy from the light. You use a PN junction. The junction is shown in the dotted black color. And you have a transparent negative material and positive material that makes the contact. And from that junction, I have explained the formation of the electrical energy by 3 band diagrams. Let me go into the photoelectric effect more details, and you may recapitulate that you have learned this process in your school level physics when Einstein explained it in terms of the photoelectric effect. The same photoelectric effect I am explaining here. Now, if a PN junction is sandwiched by the two layers as shown, the blue and the brown, top and bottom, then you are giving energy. So the carriers which are coming, that comes at is the absorption of photon, it gives you or releases the carriers, that means breaking the EHPs or helping to move the carriers, and electrons will go towards the conduction band and holes naturally eventually go towards the valence band. And these free electrons, once they will go to the conduction band, and these free holes, when they will go to the valence band, they can move towards the external contact, and once they complete their flow, you will get the electric current. So that is symbolically represented by three band diagrams. So our objective is to move the carriers, the EHPs, inside the device, and in order to give the energy along with electrical bias, it may require, may not require, but let electrical bias is 0 for that time being. I will come to the requirement of electrical bias after 1 or 2 slides. It's eventually required, but let without any electrical bias, the optical energy is sufficient to move a few carriers, and if those carriers move in the conduction and valence band respectively, then you will get some electric current, and that is represented by the glowing of the bulb. So that basically is nothing but the photoelectric effect. The name is very simple, photoelectric, so that means optical to electrical conversion, and there is no ambiguity related with the matter. So what photoelectric effect if I go to a detailed circle? So sunlight that is composed of photons, these photons are absorbed by solar cell, and then valence electrons excite after absorbing the energy and goes to the conduction band, and they become free. Sorry, one arrow is wrongly directed. However, you can take, and these minority carriers, they move according to the direction of the reverse current, and if minority carriers move, that will cause a net increase of the potential difference. Naturally, movement of majority carrier reduces the built-in potential, so movement of minority carriers increases the built-in potential, and since these carriers are moving, so you will get a generation of voltage. Because it is of optical means, so it will be called photovoltage, and the effect is called photoelectric effect. That's all. So that is given in the band diagram. This is p type and n type. You are freeing the minority carriers, so electrons in conduction and holes in valence, and they start to move, and that will give you the amount of energy required. So again I am explaining the photoelectric effect, that is sunlight composed of the photons, those are absorbed by the solar cell, and then valence electron excite due to the, owing to the fact of the absorbance of the energy, those will go to the conduction band and it will become naturally free. So these minority electrons move according to the direction of the reverse current. I will explain why the reverse current I am telling you, more than minority carriers, and that increases the potential difference because of the reverse bias, and that gives the photoelectric effect. Now the question will come, why there are minority carriers? Now if you have a device, suppose there is no bias, so if you make the generation of the carriers, maximum carriers will be generated in the depletion region. That's very simple from a p-n junction point of view. Now in depletion region, the carriers exist are the minority carriers. So if you generate more carriers in the depletion region, naturally you are increasing the concentration of the minority carriers. So the photo-generated carriers are not the majority carriers, they are minority carriers. And that concept will be totally utilized when we go for the IV characteristics, efficiency calculation, series resistance effect analysis, and elsewhere. So that point should be remembered very clearly for our perspective, and please remind the fact that the carriers generated in the depletion region, since those are minority carriers, so photo generated carriers are minority carriers. Now, one point may be given that what is the difference between photovoltaic effect and photoelectric effect. So photovoltaic effect is the effect where emitted electrons are pushed through a junction potential, where photoelectric effect there is no junction potential involved. That means emitted electrons in the photoelectric effect into a free space, whereas photovoltaic effect, electrons directly enter in another material upon emission. So photovoltaic is a different thing. Photoelectric is something else. So photovoltaic is this thing we have explained, whereas photoelectric effect you have learned in case of the Einstein's equation. So I think the difference is clear to you. In photovoltaic, you know the p-n junction requirement, whereas photoelectric effect, if you recall the Einstein's case, that the generation is for a particular material, it may be a single semiconductor or single metal, and the case of the work function is most important. So I am just explaining it. The left hand side, it gives the concept of the photovoltaic effect, where electrons are emitted from the surface or from the bulk, whereas photoelectric effect is given here, where there is a junction potential and you have to go through that, and you have to form the carriers in the depletion region and they will move elsewhere. So that's the requirement or the basic difference between them, and that should be considered for our next level of analysis. So I am coming to the IV characteristics of the solar cell. Now, consider a p-n junction under application of a bias, as symbolized in the right hand side using a blue circuit. Naturally, the red curve will explain the IV characteristics of a p-n junction diode, and I'm not going into details because you know why p-n junction diode is required. Because a single semiconductor, if you use, that will give you the photovoltaic, not photoelectric. So so there is a difference. So I think the concept is clear. For photovoltaic, you require some sort of devices actually for a junction formation, and because of that factor, so you know how to deal with. Again, if you have a problem, I am going to the previous slide. So photoelectric is means there is no junction potential, so you are emitting the electrons from the bulk and from the surface, that is the left hand side. And photovoltaic, you require some p-n junction where you are just making some optical illumination and getting the carrier. So there is a junction potential involvement in the case of the photovoltaic effect. So again, I am coming here, and if this is the IV characteristics for a p-n junction, I think it's very simple. So you know, without illumination, the equation is given, and it's a simple equation. I am not going into the minus IL factor, it will come a little bit later, but if you just neglect the factor, you think I equals to I0 exponential q v by eta kt minus 1. So this is known equation for all. I am coming to the minus IL factor a little bit later. Now I am just making a incidence of the light. So once we are making the incidence of the light, naturally what will happen, suppose you are making the forward bias of a p-n junction off, there is no electrical bias. So the photons will incident in the depletion region, and the carriers, minority carriers, will start to generate. Now, if without bias, if you get the minority carriers, whatever be the small amount, they will flow and they will cause a current. And current caused by minority carriers is nothing but the reverse current. It's very simple. So at zero bias, you will get some sort of current, and that's why the characteristics curve is shifted towards the third and fourth quadrant. Now apply some reverse bias. So if you apply reverse bias, already you are generating minority carriers. Further, you are applying reverse bias. So what will happen? You will get more negative current, and that's why the curve will shift towards the third quadrant of the characteristics. But instead of that, if you apply positive bias, what will happen? Positive bias will try to make flow of majority carriers, and negative bias will make flow of minority carriers. Now the optical illumination causes flow of minority carriers, whereas if you apply positive bias, it will cause the flow of majority carriers. So majority carriers means positive current, minority carriers mean reverse current. So there will be a net current, and if you start to increase the positive voltage without changing the illumination, that means you are keeping the reverse current constant and you are slowly increasing the forward current. So at a particular forward bias, the forward current and reverse current, they become equal. That means the net current becomes zero. So you will get a point where there is finite voltage but effective current becomes zero. And that is shown in the positive axis of the voltage. Now if you further increase the voltage, naturally the positive current, that means the forward current, starts to dominate, and reverse current, that keeping constant, so effective current becomes positive and you will get a diode like profile. So that total explanation gives you the IV characteristics of a solar cell. Again I am explaining because this part is most important among the total video lecture. So if you have optical illumination with zero electrical bias, because of the formation of minority carriers in the depletion region, total current is negative. If I add negative electrical bias at this condition, total current becomes more negative, but the value will be negligibly changed because the reverse current, the magnitude you know, is extremely small for a PN junction before breakdown. But if we add positive bias, the forward current starts to increase and there will be a net current because optical illumination gives reverse current and electrical bias, positive electrical bias, gives forward current. So at a particular point, the reverse current magnitude becomes numerically equal to the majority carrier current magnitude and the net current becomes zero. So at that point, you will get a finite voltage where current becomes zero. And if you increase positive bias more, you will get more forward current. So that is the IV characteristics under illumination condition. So if you merge them, the IV characteristics before illumination and under illumination, or suppose if you make more illumination, what will happen? There will be more minority carriers, that means more negative current, so curve will be shifted towards the third and fourth quadrant, that means it will be downward shifted. So the intensity of photons, that means the optical illumination, plays a key factor in determining the IV characteristics of the solar cell. Mind it, while I am shifting the curve, I consider that at each point our previous electrical bias value retained. That means when we are changing the optical value, we are considering the electrical bias is kept constant at a particular point. When I am changing the electrical value, I will assume that optical illumination criteria kept constant. So if you get these two characteristics curve, then if I merge them, you will get both the curves. One is dark condition, another is illuminated condition, as simple as that. So you are getting two characteristics curve. One will be dark. Dark means without illumination, which is our normal p-n junction IV characteristics. Another is the illuminated condition, which is in presence of the photons. Now, one point may be reminded that the shift between the dark and illuminated, that is dependent on the intensity of the incident photons. That means what is the illumination at that time. So that is a key factor. So that completes the IV characteristics of the solar cell. That's the graphical representation. And we have two important points, that is VOC and IOC. That means open circuit voltage and short circuit voltage. So in order to explain that, I am just going back to the, I am enlarging this, or I can go back to the my previous slide, where you will find that the current when voltage is 0, that current should be short circuit current, and that is available in the illuminated condition. That slide, it's very simple. And the voltage when current becomes 0, that will be the open circuit voltage. So VOC and IOC, these 2 points are available in the illuminated characteristics condition. So if I now take this fourth quadrant curve and reflect it towards the first quadrant, just making a mirror replica, then you can understand it very easily what is the VOC and what is the IOC. I think it's very simple, shown in the green color, that is the short circuit current when the voltage is 0, and also in the VOC when the current is 0, and that is the open circuit voltage. So the power spectrum, which is nothing but the product of the voltage into current, that is shown in the blue color in the top right hand corner of the graph, and corresponding equivalent circuit is shown in that bottom. So the maximum power, which is actually our desired point of operation, should be the product of maximum voltage into maximum current, and we have to operate the solar cell at the point of maximum power, and that point has the utmost significance while designing a solar cell. So that point should be noted very clearly, and that is given in the figure as noted down PMP. That is the maximum power point. So next comes to the analysis of efficiency or figure of merit of the solar cell. Figure of merit is defined by the term, it is the maximum power divided by the ideal power. Now what is the maximum power? I have already explained. It is nothing but product of the maximum voltage into maximum current divided by the ideal power, that is the product of VOC into ISC. And naturally from this equation you know that the denominator is greater than the numerator, so fill factor will be always less than 1 but should be greater than 0. So it lies between 0 to 1, and that's why it should be called as a figure of merit of the solar cell. So in order to understand it more details, I am showing two rectangular boxes. One is in the deep color, another is in the light pink color. So area of the A box, that means the deep color rectangular box, that gives you the Vmax into Imax. Whereas VOC into IOC, that is the shaded light color box, and that's why you are getting the point of the area, and you know that the dark color area is always less than the light color area. So fill factor will be always less than 1 but greater than 0, and that's very easily can be understandable from this figure, and that's why I have shown two rectangular so that you can just visualize and you can compare it very easily. And then comes to the conversion efficiency. The conversion efficiency is nothing but the ideal power multiplied by fill factor divided by incident power. So, and it is one is the point that it should be measured when air mass is 1.5. Now what is air mass? It will be 1 by cos theta. I think if you have a problem, you can go to the lecture on the solar time in my YouTube channel, where I have explained the air mass in details. But one can say that it is the theta is the angle between the incident ray and the vertical line, and that gives you the cos theta, and 1 by cos theta is nothing but the air mass. And when it is 1.5, at that point only the conversion efficiency is calculated, and that's a very important factor because air mass is a factor related with the sun's position. So solar cell conversion efficiency can't be measured at any sun's position. The position should be such that the value of the 1 by cos theta function should be 1.5, and that should be noted down while we have to go for the practical calculation of the conversion efficiency. So what are the loss factors related with the conversion efficiency? There are 4 major loss factors. First one is the optical losses because of the reflection and shadowing of the metal contacts. The EHP is generated due to the carrier recombination, that is a loss. So some of the EHP is always recombined. Some part of the solar spectrum is always unused because some h nu, that means some energy, may be less than the band gap of the semiconductor, so that part will not be used. And some may be greater than the band gap, that part will not also be used. So you have to take a pinpoint portion of the spectrum. Now when you are considering the spectrum, you can't make it as a band limited, a very small portion. It has a wider bandwidth. So naturally a huge portion of the solar cell will be lost because you can't make a tunable sort of semiconductor which can absorb all sort of emission. That's virtually impossible, never possible. So you are taking a very small portion of that. So now I am going to the mathematical analysis part of the solar cell. So first I am going to the IV characteristics. We consider capital G as the generation rate of EHPs by incident of the photons and capital A as the cross section of the p-n junction diode. So what are the number of electrons created per unit time within a diffusion length of p side? Please think out. The diffusion length of p side, say LE. So in the cross section, that means if I have to take the volume, so it will be A into LE. So number of electrons created inside the volume per unit time multiplied by generation rate. So it will be A into LE into G. So similarly it will be for number of holes, so it will be A into LH into G. And electrons will be created in the p side and holes will be created in the n side. Why? Because I have already explained, because it is the minority carriers. So what will be the total number of photogenerated carriers? So AGLE plus AGLH. And if I multiply the number of carriers by Q, that will give me the total photocurrent IL. So IL is the total photocurrent that is given by QAG into LE plus LH. And this is due to the minority carriers. So what is the net current? Net current is the diode current minus IL. And that is the expression of the solar cell which I have showed much earlier at the case of p-n junction diode, and I have said that I will explain the origin of IL a little bit later on, and that's the origin of IL I have mentioned here. So that gives the IV characteristics of the solar cell. Next I am coming to the calculation of the efficiency, and I will start with the IV characteristics of the solar cell. Now you know, for field factor calculation you require 4 parameters. What are the parameters? Open circuit voltage, short circuit current, maximum voltage, maximum current. So I will derive all these 4 terms and then calculate the field factor. So first I am going for open circuit voltage. So total current is 0. So if I substitute 0 in the equation, then you will get 1 plus IL by I0 is exponential Q VOC by KT. So what will be VOC? It will be KT by Q log 1 plus IL by I0, and that should be the expression of open circuit voltage. It's very simple, just direct calculation from the IV characteristics of the solar cell. Next comes to the case of power, and one point may be remind that here you should take the eta factor. So if you take the eta factor, the eta will come to the top part, that will be eta KT by Q. Similarly, if I go to the power is nothing but V multiplied with the total current. And for maximum power, the first order derivative should be 0, so we will make dpdv equals to 0. And if you differentiate, ddv of total expression is 0. Just some simple mathematical steps. I am not going into details. Just read out will be monotonous. So you solve it. And once you can solve it, I am showing all the steps in details. And the last part is most important, the last line, because from there I will show you how to get the maximum current. So we will get 1 plus IL by I0, that value. And once you will get, you can calculate Vmax. Now this is a very tricky equation. Though you are calculating Vmax, but Vmax is also available in the right hand side. This is called transcendental equation. That means x equals to fx. So x is available in both the sides and you can't solve it analytically. You have to take some numerical techniques. It's best to take the Newton-Raphson method or the convergence principle. You can approach from both the sides and it will reach to the convergent points. So that is the formula for Vmax. Next I am calculating short circuit current. It's very easy. Just put V equals to 0. You will get I net equals to minus IL. So that is the third parameter. And naturally, the expression of IL previously I have written. So what should be the part of maximum current? If you put the diode current factor is 0, so maximum current will be I0 Vmax Q by eta kt exponential that term. So that will be the maximum current. So you are getting all the 4 equations. So efficiency, that means the field factor is Vmax Imax by VOC IOC. 1 point, please multiply eta in the case of this denominator, because I am written kt by q, but it should be multiplied by eta. That's a small mistake. But once you will write eta here, you will get the expression of the field factor, and that's the very small expression of the field factor. You can easily derive it. So you are getting the field factor expression. And if you consider a theoretically series resistance Rs, so the total current will be modified, it should be reduced. So instead of QV by eta kt, you have to write QV minus Q into net current into Rs. And if you just solve it, you will get an equation V minus I net Rs is eta kt by Q log of one function. And once you will get that, you can get the expression of V. That's very important. This expression of V is different with the previous expression because this is a term I net into Rs. That term is added. That means resistance, series resistance have an effect on the applied voltage. And how it is affected, I am showing in the graph. If you have a problem, I am enlarging the slide so that you can go through it. And you will find that blue curve is the ideal solar cell and red curve is the solar cell with the series resistance. So the power output, it basically shifts. It is not now according to the blue curve, it is now according to the red curve. So maximum power point is doesn't tuning with the following the same blue curve, that is I have shown in the case of field factor. If you consider the Rs, the maximum power curve now starts to vary. And that is one of the most important factor. And for your help, I am also showing you the equivalent circuit which is showing here. And I am adding a series resistance Rs. Similarly, if I go for a factors affecting the conversion efficiency, before that I am saying what is the shunt resistance effect. And similarly, shunt resistance also, that is the red curve, which is the degraded curve, because there is a term V by RSH in the current component, and naturally it has a degrading effect. So once you will go for the practical calculation of the solar cell, you have to consider both the factors series and shunt resistance. So if I merge the effect, this equation will be modified QV minus Q I net Rs and plus V by RSH as shown here, and the curve, red curve will be further degraded. So that's why you can get the very uh, graphical idea from here that why the efficiency of solar cell is not very high. It can be limited within 12 to 15%, though the organic material now gives 44% the dye synthesized solar cell, but normally it is reduced in a very small manner. So these are the series and shunt resistances. And what are the conversion efficiency for factors? I am mentioning those. The wavelength of light, we have already understood. The recombination factors are very important. Environmental temperature, because higher temperature decreases the efficiency of the materials. The resistances, the series and shunt resistances I have already shown. And the absorbing material, that quality is very important. And open circuit voltage, that obviously increases with increase of band gap, whereas short circuit current decreases with increase of band gap. And so material basically can tune VOC and IOC. So depending on your requirement, if you know this will be my maximum power requirement, so you can choose trial and error basis VOC and IOC, and corresponding to that you can choose the material. So this is one of the very important factor, the practical output, how it is related with the material parameter. So that these 2 points are extremely important. What are the temperature effects? If you increase the temperature, that causes the increase in diffusion length and increase in minority lifetime. So diffusion and minority lifetime, that means there will be more generation of the excess carriers, more minority carriers. And more minority carriers means graph will more downshifted, and VOC will decrease rapidly because of the temperature effect, and the fill factor, that means the conversion efficiency, will also decrease. So for solar cell operation, the temperature is one of the very important factor. Now for a good photon emission incidence, you require a huge amount of solar energy. It should be a clear sky, but that also raises the temperature and further degradation of the efficiency. So optimizing factors are present in all over the cases, and these are some selected reference you can consider for going into details. And in the next lecture I will also go the optical transmitter portions and other receiver portions. Thank you all.